had any interaction with either of the math candidates that were here on Monday or Wednesday, either in person, in class in linear, or at the research presentation, or at lunch? I know Dr. Olson sent out feedback forms. If you have not filled those out already, please do fill those out as our search committee meets here at 12:30. So if you could get that done in the next hour and a half, that would be really appreciated. All right. And I do thank all of you for participating, even in class, because I know it's weird having different people come in and teach class. It's probably weird to have me come in and teach class, but I know it's strange and it's hard to adapt sometimes. So I do appreciate participating in class and those things, because I was in linear as well. So I do appreciate it. I wanted to say thank you to everybody who was able to participate. So, all right. Also, I handed out homework for next Tuesday. The header on the top is wrong. It should be say homework 2. I know this is homework 3. I had a couple of people ask, like, did I miss a homework 2? No, you didn't. It was me didn't change the header, because you'll also notice it says spring of 24 on it instead of 26. I just forgot to change the header. So you're all good. That is homework 2. So in case you were wondering, because like I said, I had a couple of people ask me about it. And no, you didn't miss anything. That was me being stupid. So it happens. All right. Any questions about anything at all before we get going? No, we're good. All happy? Happy as you can be. All right, so let's continue on with our discussion of interpolation. Pardon me. Let's, I can't remember if these are the points we had last time or different ones, it doesn't matter. Let's say we have a set of data. Let's say I've got X's and Y's. Let's say our X's are 1, 2, 2.5, 3, and 4. And our Y's are -1, -1/3, 3/32, 4/3, and 25. Doesn't really matter. We have 5 points. When we're talking about finding and interpolating polynomials, that means that we want a polynomial that goes through all of the points that we are given. That's what it means to find an interpolating polynomial. We want to find a polynomial that goes through all of the points that we're given. Okay. We have 5 points. We want to find, hopefully, a unique polynomial that goes through those 5 points. We want to find a unique polynomial that goes through those 5 points. What degree polynomial are we going to need in this case? It's 4, right? Why is it 4? Why is it degree 4? Well, think about what a degree 4 polynomial needs. If you have a degree 4 polynomial, how many coefficients do you have to find? 5. Because you got to find the constant term plus all the coefficients on the powers of x from 1 to 4, right? So the degree of the polynomial that you want is always going to be 1 less than the number of points that you have. And think about that in context of what we did last time, right at the end of class. We set up that system of equations. For those of you who have had linear or are in linear, how many solutions are possible for a linear system? 0, 1, or infinitely many, right? We want a unique polynomial. We want the 1 solution case, right? If I have, think about linear, okay? I know some of you had linear with me. Think about linear. If I had a situation where, say, I had 2 equations and 3 unknowns, and I put this in row echelon or reduced row echelon form, what am I guaranteed is going to happen? Well, I can get a pivot here, right? I can get a pivot here. Can I get a pivot in that column? No. So, and I always put a little vertical bar there when I do my augmented matrices. I'm guaranteed either I'm going to get no solution, because I could get a 0 equals something that's not 0 here, right? I could get all zeros and then something that's not. But I can't get a 1 there. I cannot get a unique solution, right? So I can't have fewer equations than unknowns, because that won't give me an exact. I'm guaranteed not to get an exact solution there, right? I can only get infinitely many if I get any. Okay, so I don't want that. So I need to make sure I have enough equations. If you go the other way, and get too many equations, you might get a pivot here, you might get a pivot here. What don't you want there to make it consistent? You do not want a pivot there, right? If you get a pivot in that final column, you've got problems, right? So you don't want too many equations, right? So if you're looking for unique solutions, typically you want square systems. And what we mean by square systems means is the same number of equations as unknowns. Okay, typically. A little bit of a linear algebra review, or maybe lecture if you haven't seen it before. Okay. But you can think about if you've done any row reduction at all, basically you're looking kind of for those diagonal ones, right? To get that unique solution. Because that tells me first variable definitely equals that value. Second variable definitely equals that value, and so on down the line. Right? Okay. So we want those square systems, which is why if I have 5 points, that's going to give me 5 equations I want to solve for 5 unknowns, which makes the 4th degree polynomial. Because I get that, I start counting with 0, right? Because I got to get next to the 0 there. All right. So last time we did this with that Vandermonde matrix, right? Right. So remember with our Vandermonde matrix, basically, again, a lot of times we set it up in increasing powers. So if I think of my polynomial that I'm trying to find, that goes from a0 up to, say, an a4 x to the 4th. Oops. That's the polynomial I'm looking for. Or f of x or a y, whichever way you want to call it, doesn't matter. Okay. We're going to plug in the x's and get out the y's is what we're trying to do, right? Or when I plug in the x's, does the coefficient on this ever change? No. So your first column in your Vandermonde matrix always looks like 1s, which is what, and in this case, I only went down 5 because the number of points I had was 5. Right? Your first column is always going to be just a bunch of 1s. Assuming we're doing increasing order here for our powers. If we're decreasing order for our powers, then our last column would be 1s. Okay. Notice the next one, we're going to plug x in and get the coefficient on the a1 we're looking for, right? So in the next column, they're literally just going to be your x values. In this case, those x values were 1, 2, 2.5, 3, and 4. For the points I just wrote a minute ago, right? In your second column, what are you going to do with each of your, well, to get the second column, what are you going to do with each of your x's in that third term? Square them, right? So the next column will be 1 squared, 2 squared, 2.5 squared, 3 squared, 4 squared. And now you start to see the pattern, don't you? What are we going to do with all the x's to get the fourth column? Cube them, good. And in the last one, we will, for the last column, we will fourth power, right? Oops, to the fourth. All right. I'll just call that matrix V so I can call it something. Doesn't matter what I call it. But V for Vandermonde. Okay. All right. So I'm trying to figure out what the coefficients are. The A0, the A1, the A2, up to the A4, right? That's what I'm trying to solve for. What's going to be on the right-hand side of my equation? What's going to be my y's, right? So if I take my v and multiply it by a0, a1, a2, a3, a4, I want to get the y values that we have, which are -1, -1/3, 3 over 32, 4 over 3, and 25. Sometimes you see this written as a v. A lot of times you'll write a matrix and then you'll write an x for the vector. In this case, the things I'm solving for are a's, so I'll write my a as my vector. It's really, really hard to write in boldface on paper, right? So a lot of times you put a little vector notation over the top of it that says that you have a vector. I know a lot of times with a vector you put a little you put an arrow that looks like that for a vector over the top of it, but I'm super lazy and don't want to go back over myself to get the bottom part of the vectors. That's why I always just do it like that. Mathematicians are lazy, so I don't want to have to backtrack and get the bottom of my vector. And then on the right side would be your constant, so I would have some vector b. Does that matrix equation look familiar? Okay. We are, in the next topic that we're going to talk about, we're going to focus on how you can solve this particular type of equation. Okay. We'll do that in the next topic. Right now I want to get through interpolation, and then I'll go back to solving systems of equations. Because bad things can happen when you solve systems of equations, so we want to talk about how those things get handled. For our purposes right now, I literally just want to solve the system. Okay? Later on, we'll talk about how do you handle bad things or how do you do things faster. Right now, I just want to solve it. Okay? Thinking about, pardon me, thinking back again to linear, or just think back to algebra 1. If you have the equation 3x equals 9, what do you do to solve for x? Divide by 3, right? Or, rather than thinking about it as dividing, you really do multiplication by 1/3. That's what dividing is, right? Or you multiply by the multiplicative inverse of 3, right? 1 over 3 times 3x equals 1 over 3 times 9, right? That's what you do, right? The reason why you do the 1/3 times the 3 is because that gets you back to 1, right? And so then you can just say that, correct? There's also an associativity step in that second step, right? I got to move my parentheses over to the 1/3 and the 3. By the way, this is why algebra is hard when you first start learning it. There's lots of rules that are just embedded in there that now you don't really think about. But if you think about when you first started learning it, there's a lot of rules, right, that you got to follow. The matrix analog of that is to multiply by the inverse, right? If you're trying to solve ax equals b, you do row reduction to start with in linear, but then you also talk about finding inverses of matrices so that you could undo multiplication. So you would do the inverse of this in this fashion, right? And then when I multiply these two matrices together, you get what's called the identity matrix. It's the matrix equivalent of 1. And so, oops, I left my A inverse off. And so you get to this point. And this gives you the unique solution, assuming it exists. Okay. I know I'm kind of glossing over this because I know some of you haven't had linear, some of you have. Well, some of you are in it now. I was there the last 2 days. I saw some of you people. Okay. And some of you had it with me. Okay. All right. There's a lot that goes into this as well. Okay. Not every matrix has an inverse. For numbers, there's only one number that doesn't have a multiplicative inverse. What is it? 0, right? Because I can't divide by 0. The reason why you can't divide by 0 is because you can't undo multiplication. 0 kills everything, right? Remember, the whole idea of dividing is to figure out where you started. Well, I can't tell where I started if I multiply by 0. If I multiply by 0, I get 0 no matter what. So I don't know if I started with 1 or 2 or -7 or pi or 1 over the cube root of 9, right? I don't know what I started with. That's why you can't divide by 0. You got infinitely many possibilities. Matrix multiplication is even more complicated because just because you have a non-zero matrix doesn't mean you have an inverse. Easiest example of that is that it's not square. You don't have an inverse. You can't have an inverse, right? But even square matrices don't have to be 0. You can get not an inverse. Easy example, take a square matrix that has all 1s in it. Not inverse. That's an easy example. So a lot of time is spent for trying to figure out when a matrix is invertible. If it is, then you can do it this way. Computationally, that's not the fastest way to solve a system of equations. Okay, we're going to talk about a little bit about that again in the next topic that we'll talk about, because that's kind of the point of this course, to do things from a computational perspective. Okay, not what I want to focus on today, but I want to give you a little bit of kind of lead into that, why we're going to talk about it. Okay. Also, to give a little bit of lead into why we might not want to solve it this way, if this were 10, I would divide by a 10. If this were 100, I'd have to divide by 100. If it were 1,000,000, I'd have to divide by 1,000,000 to get to the final answer that I want, right? Dividing by those smaller and smaller numbers makes things get really, really big. If you've got decimals in there, if you've got really, really big numbers, it's going to start kicking those decimal points off the end. You're going to lose accuracy. Just by the way we have to represent numbers. For matrices, it gets even worse. There's a thing that's referred to as the condition number of a matrix. We may or may not have time to go more in depth into that. But the condition number of a matrix basically is a measure of how close to being not invertible it is. And if it's ill-conditioned, trying to find the inverse is a really, really bad computational problem. Okay? Van der Maan matrices, I mentioned this the other day, Van der Maan matrices get really, really close to being not invertible. They're ill-conditioned, which means that the Van der Maan matrix isn't the best way to solve in general for polynomial interpolation. Okay? That being said, is what we're going to do for a couple of minutes. Okay? Because it's the easiest way to set it up, right? This makes sense for setting up the problem, doesn't it? Right? We plugged in the x's, we got out the y's, we got this nice simple matrix. And algorithmically, it's really easy to do. Right? In fact, Python has a built-in method for doing it, to set up the matrix. Okay? So let's do that real quick. We're also going to do this in Excel, because we can do this in Excel quickly as well. Okay? Other ways that we can solve these systems that are a little bit more numerically efficient in some senses. Okay? You're all very excited about learning about this today, I can tell. You're just chomping at the bit. You're so excited that I'm talking about all of this. All right. Let's import numpy as np. And I'm also going to import, since we're going to use numpy's built-in linear algebra package to do the solve command, let's also import numpy.linalg as LA, just so that I don't have to type in np dot. Oh, apparently I must have hit shift and enter at the same time. Not so I don't have to type np.linalg.solve every time I want to solve. Okay. All right. Here's the command for making your Van der Maan matrix. So it's a numpy built-in command for the Van der Maan matrix. It even tells you, generate a Van der Maan matrix. It's Google Colab will put up a little bit of documentation in there for you as well. So np.vander is the Van der Maan matrix. It'll create that for you. I think it will take a list from Python. If not, if it gives us an error, we may have to convert the list to a numpy array. Sometimes numpy's a little bit cranky about whether or not it'll take a list or an array. And I didn't check before I came in. I think I put in a list when I did it earlier, but I'm not 100% certain that's what I did. I did play with this before I came into class today, but it doesn't mean I remember what I did this morning. Okay. Why would I? All right, so our x values were 1, 2, 2.5, 3, and 4. Something you might want to get in a habit of doing when you're typing these things in, it should be fine since I put in 2.5. If you type things in without a decimal on the end, Python will recognize it as an integer, and you may want it as a float, depending on the computations. If you want to make sure that it forces it as a float, it probably is just good practice to start getting in a habit of putting a 0.0 on the end, just so that it knows to do floating point operations. Okay. To see whether or not we've created this correctly, let's put a print statement in here and just print the matrix. Looks like we're good. You can also tell in Python that it is doing floating points rather than integers because it actually put a decimal place after each of the integers that it did. If it didn't put a decimal place, then Python's treating it as an integer rather than a float at that point. Okay. How is this different than what we wrote? It's reversed, right? So if we want to put it in the same order, there is a second parameter that you can pass into the Vanderbond function that is called increasing. The default to that is false, so you can set it equal to true. And then it'll flip it around. So there it creates the Vanderbond matrix for us. So we don't have to try that. The last time when we did this, we typed it in, right, by hand. Okay. It also comes out as a numpy array, which is what you do. You do have to put things in as a numpy array when you use the solve command. Fairly certain of that. But it has to be as an array and not as a list. Okay. So when we put in our B matrix are constants. Let me call it B. I'm going to write it as an np.array so that it really knows that it's a numpy array rather than a list. And the coefficients the constants were -1, -1/3, 3/32, 4/3, and 25. Now, you know from linear algebra that you got to be cognizant of your dimensions of your matrix to make your multiplications work correctly, right? Right now, technically, this looks like a 1/5 matrix, and really we would need it as a 5/1 if we were to do the multiplication. However, NumPy is okay with putting the matrix and then the vector in this form, and it'll know to solve that you really want to make that a vertical column. You don't have to do it yourself. So you can use the solve command, but the solve command is in the linear algebra package, which is why I did that import numpy.linalg as LA, so I can just refer to it as LA. Okay. LA.solve. First thing is your coefficient matrix. The second thing is your vector. The way we have this set up, your first value is your constant. The second one is the coefficient on the x. The third one is the coefficient on the x squared, and so on. So now we have our polynomial. And you can also do things in Python. There's also a polynomial, a built-in polynomial function. But you can create a polynomial function using those as your coefficients if you want to play around with the polynomial. Right now, I just wanted to get the polynomial. There's lots of different things that you can do in here. One of the things, if you're really doing stuff like this going forward, always look to see if something's already been created rather than having to create it yourself. It's a lot easier to do it that way. Pardon me, there's lots and lots and lots of documentation online from Python and NumPy and everything else. chances are if there's something you want to do, somebody's already done it. Okay. All right. Anyway, are we okay with that setup? So now you've got your polynomial that you can play with. Like I said, there's built-in polynomial functions that you can define that way in NumPy as well, or you could define your own function using those as your coefficients. You can just run through the array. You can iterate through an array just like you could iterate through a list in Python. So if you wanted to create your own function to return whatever the x value, whatever the output is for that polynomial, you could just define your own function as well and just iterate through the array just like you would a list. Okay. All right. This also sets up pretty well for doing this in Excel. So I want to show you how you do this in Excel because you probably have not seen these types of functions in Excel before. And if you have, I apologize for boring you. Okay. All right. So let's type the points in Excel here real quick. The x values were 1, 2, 2.5, 3, and 4. And your y values were -1, -1/3. Be careful in Excel. If you don't put the equal sign in something that you want to divide by, chances are Excel is going to try to turn it to a date. Okay, so anytime you have a divided, put an equal sign in front of it, because if it turns it into a date, it will keep that cell formatted as a date. So even if you go back and try to say equals the division, it will still convert it to the date because Excel is a pain in the butt. Okay. 3/32, 4/3. Everything in Excel has to be a date according to Excel, apparently. It's really annoying. All right. So first, let's create the Vandermonde matrix. This should be pretty straightforward to do in Excel. I've got the x's over there on the left. I can just keep increasing the powers on the right, or when I make this over here, and I should be able to copy it pretty easily. Remember again that our first entry is going to be a 1 no matter what. So I'm just going to type a 1 and copy that down from my first column. The first thing is I want the x value, right, from my next column. Correct? If I go to the next cell over, I want the x value squared. If I want the next column, I want the x value cubed. And finally, the final column is the x value to the 4th. Now, it looks like all 1s here, of course, because that's what it is for the first x value. But now if I copy down, grab that little box and pull, if I actually hit the click on it, it pulls down my matrix. If I go back over to Python real quick, that should match my Vandermonde matrix that we came up with before. Okay. Any issues getting that typed in? By the way, now that you have this typed in this way, well, if you need to expand it, you'd have to add more columns, but you should be able to change these numbers over here and it'll change automatically over here. Once you've got this set up, it's just a matter of tweaking it slightly to change it to different problems. Okay. All right. Let's go back and think about how we said we could solve the system, right? Remember I said that if I had the system AX equals B, if I can take the inverse of the matrix, then my X that I want is A inverse times B, right? That's one way to solve it, if I can find the inverse. Turns out this is not the best way to solve in practice, okay? But this is what we're going to do for now. Okay? All right. So in Excel, there is a function that's called the matrix inverse, or minverse, if you will. You start typing MIN, you can see it right here. Matrix inverse. before I do anything with this, this is an example of what's referred to as an array function. You're going to input a range of cells, and it's going to output a range of cells. Okay? It used to be the case that if you had an older version of Excel, you actually had to highlight the right size that you wanted the array to come out as and hit Control-Shift-Enter before it would actually do it. Otherwise, it only put in one entry in the upper left corner. They've made it a little bit better. You only have to put it in there and it'll fill in the rest. And you'll see what it looks like when it does that here in a second. I want the inverse of my Vandermonde matrix. So I'm going to highlight the whole thing. Okay. Literally I just clicked up in the upper left-hand corner, dragged to highlight the whole thing. You can also type it in if you want. Doesn't matter what you do. Okay. Once I hit enter, you notice that it fills in the whole thing, and you see that little outline piece, right? That is denoting that it's an output for an array function, and it came out and spit out a whole range of things rather than a single number. Most functions that you've probably dealt with in Excel before spit out a single number, right? This spits out a whole range of numbers. Okay. We could go back just to show that this really does match what you get in Python, assuming I remember the command correctly in Python. I can go back over here. If I do, I think it's just v.inv, remember right? Let's see if I'm right. Nope, it didn't like that. How about la.inv of v? Let's try that. There it is. So la.inv in Python will give you the inverse of the matrix. I did not play with that before I came to class today. But that should match what we just got in Excel. Just trying to show you a few new commands today. You're all thrilled, I can tell. Okay. But again, if you compare the two, you should have the same values. All right. Last thing, we said that we wanted to, let me zoom out just a little bit so everything fits on one screen. We wanted to solve this system. What we found was the inverse of the Vandermonde matrix that we came up with. To solve the system, what do I want to do with that matrix? I want to multiply it by the what? The y vector, right? Okay. My y's are over there on the left-hand side of the screen. To multiply two matrices together, there's a command in Excel to do that. It's the mult command. It's M-M-U-L-T. Mult. And like minverse. Okay. Good news is that once you start typing, if you think you know remember or know what the function name is, once you start typing it, Excel will come up with a whole list of things that says, hey, this is what these functions that I have that start with those names. Okay. M-M-U-L-T, mult, sorry. I want to take, and I have to do this in the correct order, and the dimensions have to match correctly. Okay. Unlike Python, where I said you could put the solve command, and if you had your array going in as a row, but really it should have been a column, Python can handle it. Excel cannot this way. Okay. So I really do need those y's vertically to be able to multiply by the inverse that we just came up with. Okay, so again, first, we'll highlight the inverse. Notice something interesting happens when you highlight the inverse there. Remember the output was an array. Look, it puts a little hashtag in there, right? Noticing that the output there was an array of things, okay? Rather than, usually when you have a range, it puts the first cell in the upper left-hand corner and the second cell in the right-hand corner, right? If it's the output for some array function, it outputs it slightly differently on the screen. And then we want the y's. The y's here have to be written vertically. If you have them in there horizontally, it will do it wrong. Okay. The good news is that if you have them written horizontally and you don't have to retype it, there is a transpose command in Excel as well. Okay. So you can actually do the transpose of the thing and it'll do it correctly. All right. Anyway, again, that's an array function, so it spits out the arrays. Those should be the exact same coefficients that we came up with on Python. So now you have two ways to do this. Aren't you excited? Could have also done it on your calculator. Woo! One of the reasons why I do Excel is I'm guessing these are things in Excel that you have not seen. It's one of the reasons why I like to do this in Excel, so it gives you some more exposure to things in Excel. Honestly, I mean, obviously, computers have been great for computation, but for sheer arithmetic power, the spreadsheet's probably been one of the most important advances in that. Probably in history, but we're definitely in the last, say, 30, 40 years. If you want to do arithmetic type functions quickly, spreadsheets are wonderful for that. Okay. If you want to do harder computations, spreadsheets aren't so wonderful. Okay. You can do linear algebra types of things with Excel. It's just very clunky. For example, there are row reduction types of things that you can do in Excel. It's just kind of a pain. Okay. But tabulation of arithmetic computations, spreadsheets are fantastic. They're great computational tools. If you're going to do anything with data, you should know spreadsheets and other programs as well, but spreadsheets you should definitely know. All right, anyway, questions on either the setup or the computations? Are we okay with both? Because we're going to change some things up. Okay. All right, so I've already mentioned that from a computational standpoint, generally speaking, van der Waals matrices suck. Okay? The reason why they suck is because if you get a larger and larger and larger system, your columns of your matrix get closer and closer and closer to be linearly dependent. Again, I kind of drew that picture last time. Remember what you're really finding, for those of you who have had linear, not for those of you who are in there currently, but you'll talk about it this semester. When you have had linear, what you're using is a standard basis for a polynomial space. You're generating all the polynomials from the set 1, x, x squared, x cubed, x to the fourth, and so on, using that standard basis. Turns out that standard basis is not the best representation in this case, because remember when we drew the picture last time, what happens is you get higher and higher powers. It's really, really flat, and then it gets steep. Then really even flatter, and then even steeper. And then really, really flat, and then even steeper, right? So you're going from 0 to 1. These things are getting really, really close to 0, which is what's making your columns be closer and closer linearly dependent, because they're all getting closer and closer to 0 there on that flat spot. Okay. Also, for those of you who have had or will have or are taking linear differential equations, the steep part also sucks. Computationally speaking, that spot also sucks. Get close to asymptotes, get close to boundaries. That's really, really hard to compute. Okay? So both of those perspectives are bad for computations. So we want to try to find other ways to do these polynomial interpolation types of things. None of them are great, by the way. I mean, none of them are great in all instances, I should say. They have their functions. They're their place for different things. Van der Waals matrices are just fine if you got a small scale thing that you're trying to do. If you're just trying to do cubics or quartics and that's all you're trying to do, you only have a few points, Van der Waals matrices, use it. It's fine. Works great. If you've got 500 points, don't use it. Okay? In fact, if you have 500 points, use linear regression. Don't use regression. Use a least squares method. Don't try to actually fit it exactly. We'll see why later. Not today, but we'll see why you don't want to try to fit things later, or exactly if you've got lots and lots of points. Okay? Puts too many restrictions on your polynomial. All right. Anyway, so the focus for today is to come up with two other ways to try to solve systems. One is a really, really straightforward way, and that's what's referred to as using Lagrange polynomials. All right. It's a really, really, really simple idea. Okay? So, let's say, just as a picture here, I'll draw just 4 points. I can extend this to however far I want. Okay? So I have x1, x2, x3, x4. Here's my goal. First, this is my first goal, and then we'll change this goal up slightly. Okay. First goal: find a polynomial that outputs 1 at each point. Obviously, when I get done, I don't want 1 for each of those points, because otherwise it would be flat, right? We'll talk about scaling it here in a second. But what I mean by this is, I plug in 1 into my polynomial, or excuse me, I plug in x1 in my polynomial, I want 1 to come out. I plug in x2, I want 1 to come out. I plug in x3, I want 1 to come out. So on down the line. Let's focus on each individual point first. If I plug in x1 here, if I think about just one polynomial that does that, if I plug in x1 here, I want to get a 1 out. If I plug in an x2 here for a different polynomial, I also want 1 to come out, right? If I think about at the end, I want to add these things all together. If I can get 1 to work here, 1 to work here, and so on down the line. If I plug in x1 here to get a 1, and I move to the next one, if I want to keep everything the same, what do you think I want to get when I plug in x2, or excuse me, plug in x1 into this one here at x2? What do you think I want to get out? 0, yeah. Because I want to try to piece these things together, right? So if I put in the x1 here to give me a 1, I don't want it to give me a 1 at the other spots. I don't want it to add anything. So if I put an x1 here to get 1, I want it to give me 0 here, 0 here, and 0 here. And then likewise for the other ones, right? I want x2 to give me a 1 here, but 0 here, here, and here. And then I'm going to add them all together at the end. And then it'll work, right? So that's my next goal. I'm going to refine my goals here, right? I want to do 4 different polynomials. Okay? The first one will give me 1 when I plug in x1 in the first spot, and 0s for the rest. And then change it to x2 and give me 0s for the rest. And then I'll add them all together. Okay? All right. Let's think about how we can do that. Okay? All right, so I'm going to write this down so I have it in the notes here. So, goal revised. At each point, we want f of x sub I to equal 1. At each point, whatever. At x sub I to equal, right, at each point, xi. Right, make sure I refer to the point. I want f of xi to be 1 and f of xj to be 0 when j is not equal to I. Okay. All right. So again, let's just focus on one point, and then we'll refine it for each of the rest of them. Okay. So let's just focus on the first point, and then we'll refine it to do the rest of them. Because once we do one, it'll be easy to get the rest. Okay. All right. I want a 1 to come out. Well, let's not worry about a 1 to come out to start with. Let's literally think about, I want 0s to come out when I plug in x2, x3, and x4. Okay, so I want f of x to equal 0 when x equals x2, x3, or x4. And we're doing polynomials. Okay? If a number is a zero of a polynomial, what has to be a factor? So, for example, if 2 is a zero, what has to be a factor? College algebra topic. When we have factors, you have x minus something, right? Or x plus something, right? If 2 is a zero, what has to be a factor? X minus 2. It's the factor of the polynomial, right? Yeah, the minus 2 is coming from the fact that x minus 2, right? So if 2 is a root, x minus 2 has to be a factor. If 3 is a root, x minus 3 has to be a factor, right? They go hand in hand. I want x2, x3, and x4 to be roots. So if I want those to be roots, when over here, what better be the factors? You just told me a second ago. Good. Wonderful. I want x minus x2, x minus x3, x minus x4. That gives me what I want, right? Remember, at this point, when I plug in x2 or x3 or x4, I want 0. That does the job, doesn't it? That does part of the job. It does that part that I want, right? When I put x2, x3, and x4 in, I get 0 out, right? Before we go on, what's the degree of that polynomial? Third. How many points do we have? 4. Is a degree 3 polynomial what we want for fitting those points exactly? Yeah, it is, isn't it? I've got the right degree, too. Cool. I get that for free. I'm going to end up getting that for free. Okay? That's a good thing. All right. Are we okay with that giving us zeros when we put in x2, x3, x4? Am I guaranteed for that to give me a 1 when I plug in x1? No. How can I turn it into a 1 when I plug in x1? What would I like to divide by? Well, I want the output to be 1 when I'm done. If I put in x1 for x, I want the output to be 1. Yeah, and x1 minus x4, right? That will get that'll line those things up perfectly, won't it? It lines it up perfectly, doesn't it? Yeah. So that gives me a piece of the puzzle. We're getting closer. Okay? But I do want to stop and make sure that we're all on the same page with this. Do we understand now that this gives me a 0 when I plug in any of the other x's and a 1 when I plug in x1? Is that okay? Maybe. I know our guest speakers like to do the thumbs up, thumbs down. I like to do the maybe just because it looks stupider. Okay. All right. Okay, so we'll fix the other points here in a second. But let's concentrate on what this outputs at x1. We've designed it so far for it to output 0 when I plug in x2, x3, x4, and 1 when I plug in x1, right? But that's probably not the output I want, right? I'm being very, very fixed on what I want there, right? I want this to be more general. I really want this to be f of x1 there, right? We agree? Whatever that function happens to be. Maybe I'll call it y1, just so I can refer to it a little bit nicer. Okay? Well, we just designed a function so that when I plug in x1, I get 1. How can I modify that so that when I plug in x1, I get y1? Yeah, multiply by y1. Fantastic. That's exactly what we're going to do. Yeah, cool. So to get the output at y1 at x1 to be y1, we use f of x equals y1 times x minus x2, x minus x3, x minus x4 over x1 minus x2, and my voice squeaked, x1 minus x3 and x1 minus x4. Cool. That works for 1 point. We got 3 more to go. But the other 3 should be pretty straightforward. Now that we found the first one, we shouldn't have to work so hard, right? What's missing in the top? What x value do you not refer to in the top? x1, right? So if I want to move to the x2, which x value do you think you don't refer to in the top? x2. Move to x3, don't refer to x3. Move to x4, don't refer to x4, right? So in general, to fit x1, y1, I shouldn't say fit, to interpolate x1, y1, x2, y2, all the way to x in, y in, we can do the following. We use f of x equals, I got to do a sum of a product. Okay? Using a capital sigma denotes a sum. Using a capital pi denotes a product. We need to sum up over all of our points. So we go from I equals 1 to n. We also need to multiply from I equals 1 to n, except, nope, I need a j equals 1 to n, except I don't want to use I. Because remember again, what did we say? If we were at x1, we don't use x1. If we're at x2, we don't use x2, right? Okay. In the numerator, I'll have x minus x sub j, and in the denominator, we'll have x sub I minus x sub j. That's the formula. Oh, I forgot something. What did I forget? I forgot the y value, right? I need y sub I. That formula looks ugly. Don't think about formula. Think about what you're doing, right? I'm putting all my factors on top. That'll make sure that I get zeros for all of the ones except for the point that I'm working on, right? That's why we have the j is not equal to I. We divide out by this piece to make it scale to 1, and then we multiply by the function value to make the function value agree. And we add all of those together, because the only thing that's going to change when I plug in the other points, I'm going to get zeros, right? I'm going to get the right function value at the end. And then we'll add them all together and make one big long polynomial. Okay? So if we were doing this for the polynomial, or the example that we had before, I'll just write down the values again. We had 1, 2, 2.5, 3, and 4. And we had -1, -1/3, 3 over 32, 4 over 3, and 25. I'm going to have I'll have 5 chunks, but each of them will have will be a 4th degree polynomial, right? So the formula, like I said, that's the formula, but that's not what we're ever going to do. Okay, I'm going to make this. We'll have -1 out in front, right? Because that's the function value. I'll have a numerator. How many terms will be in the numerator? How many factors will be in the numerator, I should say? 4, because there's 5 points, right? So we're going to have 5 terms. Each of them are going to be products of 4 factors on top and bottom, okay? The numerator will look like x minus 2, x minus 2.5, x minus 3, x minus 4. In the denominator, we'll have 1 minus 2, 1 minus 2.5, 1 minus 3, 1 minus 4. That's just the first one, right? Plus 2 times. What goes in the numerator? The x minus 3 and the x minus 4, right? Remember, again, in the numerator, you leave out the x value you're on. Yeah, Trace. Oh, shoot, that's not 2. My bad. It should be a negative a third. It's the function value. Sorry, thank you. It came from my rear end. I don't know. I pulled it out, Ta-da! What goes in the denominator? Yep, and so on. Yep, good. Right? We got 3 more terms to write. What should go out so I don't screw it up this time? What should go out in front of your fraction this time? 3 over 32. What x value is missing in the next set of factors? The 2.5. Good. Yeah. So I have x minus 1, x minus 2, x minus 3, x minus 4, 2.5 minus 1, 2.5 minus 2, 2.5 minus 3, 2.5 minus 4. We see the pattern? In the next one, you'll have a 4/3 out in front. The 3's missing in the numerator. X minus 1, x minus 2, x minus 2.5, x minus 4, 3 minus 1, 3 minus 2, 3 minus 2.5, 3 minus 4. You'll know if you screw it up if you divide by 0, right? And then finally, the last one was 25 times x minus 1, x minus 2, x minus 2.5, x minus 3, 4 minus 1, 4 minus 2, 4 minus 2.5, 4 minus 3. All right, for just a second here, let's think about advantages and disadvantages of this over the previous method that we just did. Tell me an advantage. There's no matrix. We didn't have to solve squat, right? This is an algorithm for finding the polynomial. And notice, by the way, I said the polynomial. As long as we have a distinct set of x values, there's exactly one polynomial of degree, and if there's n points, there's exactly one polynomial of degree n minus 1 or less that goes through those points. Does that look like the polynomial we came up with? No, but I promise you that's the same polynomial that we came up with earlier. So what's the disadvantage? That's a lot of x's. That's a lot of computation, right? If I actually try to use this polynomial for evaluation, there is a crap ton of evaluation you have to do, right? This is a polynomial of degree 4, but if I use literally this form for evaluation, I've got to do 4 multiplications 5 freaking times. That's not computationally efficient, okay? So this is great for finding the coefficients that you need for the polynomial. Terrible for using it in practice for computation. Advantages and disadvantages, right? What was the advantage for Vandermonde? It was very easy to set it up and solve it, right? What's the disadvantage? Bigger systems, harder to solve, can make inaccurate approximations. There's trade-offs for everything. Okay. Now, just for a quick definition, then we'll talk about one more interpolation technique here quickly. Each of these pieces without the function values, each of those pieces, so right here, I'll put it in red, right here. This is called a Lagrange cardinal polynomial. The only thing that's different is that's the polynomial that gives you a 0 or a 1. Okay? So without the sum and without the multiplication factor out in front, just the polynomial they came up with that gave us the 0 or 1, that's called the Lagrange cardinal polynomial. That's just the name. Okay? All right. Last part. I'm going to call it Newton interpolation. May not get through all of this. You know what? I'm just going to go ahead and say it now. We're going to move your homework to be due next Thursday rather than on Tuesday. Because I don't want to rush through this part. We're not going to get through it. We'll just change it to Tuesday. Okay? All right. So again, we're looking at the trade-off ideas here. Okay? So far we've had one system. We set up a system of equations, solved the matrix equation, right? Said that can get sucky for solving systems of equations. Okay? Then we came up with a method of have no systems to solve at all, but the computations can be bad if we're actually trying to use it in practice. Okay? So this one kind of tried to mitigate the two. Okay? We try to make it a little bit easier system to solve, but not make it so computationally inefficient. And we're trying to play the odds between these two things. All right. So here's the idea behind this particular method. Okay. We've got, I'll say, I'm not going to do numbers. Let's just do x1, y1, x2, y2, out to xn, yn. Okay. We're going to start with the first point and build up from there. Okay? So starting from the first point, what is the easiest possible function that you can think of that absolutely 100% certain goes through the point x1, y1? Easiest function that you could possibly think of. Okay, so well, y equals x definitely works, right? But what's even easier than that? Because that is degree 1. Can you think of a degree 0 polynomial that'll work? Just a constant function, right? I can just set the functions equal to the constant. That's probably the easiest possible function that we can do, right? Okay? F of x equals y1. The end, right? Agreed? All right. Let's go to the next one. I don't want to change this, right? Don't want to change that at all. Okay? Can I add something to this to where I can, well, let's say, think of something with a factor in it, so if I add it on here, I don't change anything. I'm going to make the degree go up by 1, but I want to add a factor, but I don't change this what I get when I put in x1. I don't want to move the y value when I put in x1. What factor can I add on the end so that I don't move the y1 at all? I want to think about it as just a degree 1 factor. What can I put on the end so that I don't move the y1 at all? Kind of think about it what we did earlier. I wanted to get a 0 out, right? What did I do to get a 0 out? Yeah, the x minus x1, right? Okay. Now, same idea. Same idea. I want to, this isn't going to give me what I want. It's not going to give me y2, right? So I'm going to have some sort of a coefficient here to solve for. I'll call it an a1 to start with, because we're going to figure out how to find those a1s, the a sub n's, I mean, a sub i's. Okay? But for certain, this gives me y1 when I put in x1, right? And I can adjust the constant so that when I put in x2, I get y2. I can find the constant. We'll talk about how we find that here in a second, right? But I can certainly do that, right? And it doesn't affect the y1 here if I put an x1, because I get a 0 on this, right? We agree? Okay. So what about the next one? Now I want to go to x3. What do you think I'm going to add here for factors? If I've got this y value right when I put in x1, and this y value right when I put in x2, what do you think I'm going to add in here for factors? That's fantastic. X minus x1 and x minus x2. Exactly. Yeah, that's exactly what we're going to do, right? Again, we'll have to adjust it with something. So I'll call it a2 for the time being. Right? Agree with that? Okay. And we keep going. We'll have an a sub n minus 1 there. I probably should have started with x naught, y naught, and then everything would have matched up nicely with the subscripts. And then you'll have an x minus x1, an x minus x2, all the way out to an x minus x n minus 1. And then you'll end at xn. Now, I know I already wrote y1 here, but let's just think of this as a naught for the time being. Think about the equations that you would set up now to solve. The first equation would be when you put in x1, you just get a naught, right? So you'd have to have a naught equals y1. That would be the first equation. I should write it the other way around. The next equation would be y2 equals a naught plus a1 times x2 minus x1. Right? If you put in x2, all the later terms fall off. Right? The only things you have are the a naught and the a1 times x2 minus x1. That has to equal the y2. The next one will be a naught plus a1 times x3 minus x1 plus a2 times x3 minus x1 times x3 minus x2. Right? And you would keep going. I'm going to scooch that over a little bit. I know, there's a lot of writing. Lots and lots of writing, I know. It looks ugly. But let's think about it from a system of equations idea. Is that equation hard to solve for a naught? No. Once I have that number, is that equation hard to solve for a1? No. Once I have those two numbers, is that equation hard to solve for a2? No. And so on down the line. So the solving becomes a lot more efficient. It's just substitution. we actually refer to this as forward substitution, given the way the system is set up. You've probably done back substitution, where you find the last one and you work up to find the second to last one, work up to find the third to last one, and so on up the line. This is just the reverse of that. It's forward substitution. Okay? This is referred to as a triangular system, and there are much faster methods for solving triangular systems than systems in general. Okay? So this triangular system is faster computationally to solve than the van der Waals system is. So we're using what's referred to as Newton interpolation here. We'll hear Newton a few more times. We've already heard Newton's method and Newton's interpolation. We'll have to do a Newton-Cotes method for doing integration later on. Okay, Newton's all over the place. All right. Anyway, this sets up your system. Now, notice I've got the A0 equals Y1. That's nice, but notice I don't have the A1 is Y1, or the A1 is Y2, right? But I can solve it. Let's see what it looks like. If I solve for A1 here, I would need to subtract the A0 over, but A0 is the same thing as Y1, right? And then I would divide by X2 minus X1, right? Is that a huge surprise, by the way? If I only had 2 points and I was trying to find the interpolating line between the two, what is that? It's the slope. Not a huge surprise if that came up, right? Okay. If you plug, it turns out that if you plug this in and do some algebra, your A2 becomes, it'll be Y2 minus Y1 over, let's see if I do it right. I'm going to make sure I write it down right because I don't want to mess it up for later. I'm going to pretend like I did it right. Y2 minus Y1 over X2 minus X1 minus Y1 minus Y. These are threes. Sorry. I knew I was going to mess it up because I don't have my subscripts matching. There's a pattern. Do you see the pattern? I mean, it's not exceptionally nice, but do you see the pattern? Kind of. I've got kind of that slope of the line between the second and third point, the slope of the line between the first and second point, and then divided by the difference of those outer x's. Okay. This is what we get. This is the method of divided differences. It's referenced in your homework. We'll do a more explicit example of divided differences. In particular, we're going to let Excel do it for us because this would be a nice way to put it in Excel. Okay. There's a special notation for these different things. Like I said, we'll do this next time. I just ran out of time today. Sorry. I was going to get through it today. I didn't. Stuff happens. Expletive happens. You know. Right. Have a good one. We will see you on Tuesday. Again, if you haven't filled out the feedback for the candidates, if you could do that in the next 15 minutes, I'd really appreciate it. Again, you should have an email from Dr. Olson for that. Have a good one, everyone.